Okay, so questions on I sent the report cards like a few minutes ago. So you can check them after class or something. Keisha, I'll look for your paper. Apparently I left it. So the report cards, not all grades are updated. Like I only have like one attendance grade in so far. I just gave everyone 100% for attendance so far, so that's going to be skewing things a little bit. And there are a few grades that need to be updated, but in general, you have a bunch of homeworks in there. I'm only dropping 2. I have more than 2. You can put it in there. I have more than 2 quizzes. And put it in there. I'm dropping 2 quizzes. Yeah, your test grades are already in there. So not super updated, but it's gonna give you a fairly accurate picture. Like even after I update things, it won't swing too far. When I update it later in the week, yeah, it'll still be roughly the same thing. So it's a really good approximation of how well you're doing so far. If you're not doing well so far, which means you have under a 60, which by the way, if you got less than a 60 in the exam, you should come talk to me. But if you have less than a 60 overall, that means you're pretty much failing. The last day to drop, by the way, is next week, Monday. So you have a lot of thinking to do between now and then. It depends on the individual, but personally I think the easiest part of the course is already behind us. So if you're not doing well so far, you might want to, if you're going to stick around, you have to make some drastic changes. So, and you can talk to me about those if you really want to stick around. Yeah, so moving on, we're going to be focusing a lot more on theory, a lot more on proofs. Calculations are going to be pretty much incidental, you know, but actually talking about the theory is going to become more and more important. So those of you who are not really into the theory, it's going to get a lot harder as we move on. So that's just a thing. In general, also, I round up to the next whole number. So, I mean, if you're on the verge of a new grade and you're on, like, you know, if you have like a 69.3, I'll consider it a 70. So you'd actually technically bump up where I'm not going to kill you over 0.7%. But yeah, but other than that, there's really not much leeway because I already built a curve into everything. Like a 60 is a pass instead of a 70. Yeah, that's just something to think about. And if you got less than a 60, you should really talk to me. And if you have less than a 60 overall, you should also talk to me because you really have a week to make some really big decisions. Other than, yeah?
How do you know that you have the 60 or above?
The reports that I sent you, it's in your email.
Yeah, it's just that for me.
No, like everything is there. Like you'll see what I have for all your grades, like everything.
No, because I only just got the one grade by itself.
No, there's a different tab that you have to go to.
Go press menu, go back to menu, and then go to grades.
Yeah, you'll see all the homeworks. Right, so if there are any mistakes, if you realize that you did a homework that there's a 0 for, you can, like, you should be able to see all the grades that I have in there. So it's not just the overall. You should see the grade breakdown as well. Yeah, so other than that, again, if you have any questions about that, you can email me. If you have questions about your test, you should see me after class. I really just want to jump into things right now. We have homework for 4.3. So let's jump into that. I feel like there were a lot of proofs in this homework, was that? From what I remember. I don't know. So what are we doing here? The computational ones shouldn't be that bad, so you can probably just skip those. Yeah, so what number? 25. What does it say?
S is the vector B1, B2, BR.
B1, B2,
B2, BR.
dot, BR.
Is linearly independent set.
And it's linearly independent? Independent?
Independent, yes. Of vectors. Then
Yeah.
so it's every non-empty subset of S.
Oh, so
Is every non-empty subset of S.
So, let's talk about subsets, non-empty subsets. So, proof. Let's talk about singletons first. You know what a singleton is? Set with one element. Right, so I'm talking about the sets like V that only has V1 or only has V2, etc. Right? So note the zero vector is not in S. Right? How do we know that?
Empty set.
Is that an element, the empty set is not in your sample set?
No, the zero vector is not one of the V's. How do we know that?
Because there's nothing in it.
No, zero is a zero vector. There's a theorem in the book that if 0 is in a set, then the set is dependent. That's a theorem in the text, right? 0 cannot be a member of a set, otherwise it's dependent. Because you can always write 0 as a linear combination of all the others, right? Just choose all your coefficients equals 0, and the coefficient of your 0 vector is any non-zero number. You can create a linear combination that's not all zeros, and you get this guy as a linear combination of the others. So 0 cannot be in any set. If your 0 vector is in a set, it's not a linearly independent set. So I know none of these are 0. There's also a theorem. And the proofs of these are not difficult. I think even the homework actually you had to prove parts of this theorem. Also by that theorem, we know that a singleton is linearly independent if it has a non-zero vector. In fact, if and only if. So this means all singletons are independents. Right? So that's actually the proof for, if I only take a subset that has only one element, I know it's linearly independent because that element has to be non-zero, and there's a theorem that says if your set only has one element and it's non-zero, it's automatically linearly independent. Right? Because the only way to get 0, if you take C1 times V1 equals 0, the only way to make that 0 if your V is not 0 is if the C1 is 0. Right? That's a theorem from when we started vector spaces. That's a theorem from 4.1. Yeah, it's going to be important to remember the theorems. Okay, so yeah, so in the singleton case, that's if we only take subsets that have one element, they're automatically linearly independent because the element has to be non-zero that's in there, and the theorem that says that's non-zero. Now let's suppose, let's take larger subsets. Suppose B is equal to B1, B2, up to Bn, which is a subset of S, right? So I took some of the vectors from S and I create a subset with it that has more than one element. Now I want to prove that this set has to be linearly independent. For the time being, what I'm going to do is I'm going to write S in this form, right? All those guys that I take in the subset, I'm going to list them in front, and then the rest of the guys, I put them at the back. So at this point, I would have Vn plus 1, Vn plus 2, all the way up to Vr. You guys see what I did? I arranged the set in such a way that the guys I'm taking to make the subset, I put them all at the front. These guys, I rename them by B, and then I list the rest of them at the tail, right? So they're just a set of vectors that I'm taking out of S to create another set B. Now I want to show that the set of B's are linearly independent. How do I show that a set of vectors are linearly independent? We need to show. What do we need to show?
The coefficient will not equal 0.
What coefficients?
In the equation.
What's the equation that I should
K1,
use?
B1 plus K2, B2 and so on equals 0.
I want to show that this equation has only K1 equals K2 equals Kn equals 0 as a solution, right? That's the point. Right? Once I can actually show this is true, I would have proved that B is actually a linearly independent set. How would I go about proving that? Ideas.
Who are these linear vectors?
B is linearly independent. So you just
What's
add
linearly independent?
B, right? Is B.
Begging the question. I want to prove B is linear independent. I cannot
Okay.
assume it's linear independent.
Assume correct.
Assume what?
You can start with assuming that B is
S is linearly independent, right?
I know S is linear independent.
Okay,
yes.
then you just add Vn plus 1, I mean 0 Vn plus 1 plus 0 Vn plus 2 till 0 Vr to that equation. You can add 0 times the other vectors of S.
Almost. You wouldn't want to say 0 times it.
0 0 Vn plus 1 plus 0. You just add in that.
How would that help though?
Then, since S is linearly independent,
Yeah.
all of scalars, including K1, K2, and all that zeros has to be 0. Because of that, K1 to Kn has to be 0 too.
The problem with that is, again, this is sort of the same kind of mistake that we ran into with that whole A transpose A equals A kind of thing. You're like, oh, A had to be the identity.
No,
You don't want to identify the constants. That
No, I'm
gives
not
you a lot of
identifying anything. I'm just saying.
You are. You're identifying the constants of all these V's, saying that they have to all be 0.
No, since S is linearly independent, I'm just, you're saying we need to show K1, B1 plus K2, B2 till Kn, Bn is 0.
Yes.
I'm just gonna add 0 Vn plus 1 to the both of the equations there. Can I?
That's close, but it's not. Okay, so we set this, right? So we have K1, B1 plus K2, B2 plus Kn, Bn plus, now you're taking 0 Bn plus 1 plus 0. Can I get rid of this? Bn plus 2 plus 0 Vr. Okay.
Yeah. Then whole case has to be 0, since that's linearly independent set of vectors.
Okay, so the problem that you identified this as 0 is the problem that I have with it. You don't want to do that. What I would have done is something like this, which is pretty fine. Set this to be Kn plus 1, right? Let's not assume it's all 0. Kn plus 2 This would be KR. Right. So now what can you say here?
All case 0.
Since S is linearly independent, right? So I just created another, I'm using the fact that S is linearly independent. So I set up these equations, but now I just order it a different way and I rename some of the guys, right? I'm not doing anything, right? So this means that which is sort of a kind of a jump. How a lot kind of happened here, but how I probably would have phrased this proof is to kind of do a proof by contradiction. Pretend that it's non-zero, right? Like there's a non-zero solution, and then it will contradict that this has to be all zeros. That's probably how I'd approach it, because this does require some explanation to make that jump. The idea that you're assuming these are all zero, it's not really a habit you want to jump into, because as you've seen before, it can lead to errors, right? You don't usually want to identify people unless it's like an existence proof, right? If I want to prove that there exists this particular kind of thing, then you can jump in and say, here's a specific example that does it, right? But when you want to prove something in general, be careful not to identify things. You can run in a lot of trouble. Personally, how I would have done it is I would have said something like, assume to the contrary that they're not linearly independent, then there are non-zero solutions to this, and then I can add that, and then I would get that this has to be dependent, which would contradict the original assumption. So I would have done something like that. Yeah?
So I'm just going over what the question is. So we have this set B. It contains.
It's contained in S. Yeah.
And its elements are B1, B2, all the way up to Bn. And then we said we write it as, but where does the Vn plus 1 Bn plus 2 Br is it coming in from?
That's from the original S, right? S is V1, V2, all the way up to Vr.
Okay.
I'm just saying I took the first bunch of guys and I renamed them into V's.
Okay.
Right? And then there are the rest of the V's over here.
Gotcha.
So I created my subset by pushing everyone to the front that I want to make my subset out of, right? And I want to show that setting a linear combination of those guys equal to the zero vector will only have the trivial solution. That's what I wanted to show. But then we're going to use the fact that if I take all the vectors in S and set that equal to 0, that will give me the trivial solution. So my B's have to be the trivial solution. It's basically going to be the way I do it. Probably the cleanest way to do that, I think, here would be a proof by contradiction. If I was writing down the solution, that's what I would have done. So I would have said, suppose it's actually linearly dependent, then there's a non-zero solution for these guys, in which case I can add this guy, and then I would have a non-zero solution here, which contradicts the fact that S is linearly independent. So maybe I should write down that argument, because I actually prefer that one. Because this one kind of requires some jump. If you wrote this down in a test, I'll give it to you, but I'll have doubts as to whether you really understood what happened. So let me write out what I would have done. That seems to me to explain it better. I would have said something like, assume to the contrary that B is dependent. Induction would probably also be a nice way to do it now that I'm thinking about it, right? Induction would also be a nice proof. So, and we consider K1B1 plus K2B2 all the way up to KNBN plus KN plus 1 VN plus 1 all the way up to KRBR equals 0. You can find a non-trivial solution. Namely, and now here I'm going to identify that non-trivial solution. B1 to Bn are the non-trivial solution to 1, and now we can set K1, Kn plus 1, Kn plus 2, all the way up to Kr equals 0. This contradicts the fact that S is linearly independent. So, again, going over this, the first part, proving for each individual set, it's easy because you can just use a theorem in the book, which this would be my base case if I were doing it by induction, and I would continue from that. Now I want to extend this to any list of vectors in S. And all I did was, just to keep things clear about who I'm talking about, I rearranged them and I renamed some of the guys. I'm renaming the guys who I got to pick the subset from S. Now I need to show that this equation only has the trivial solution. So several ways to go about this. One of the cleanest ways I can think about, personal preference I guess, is proof by contradiction. Assume it's dependent, which means a non-trivial solution exists. If a non-trivial solution exists to that, then I would be able to find a non-trivial solution to this. And if I find a non-trivial solution to that, that's a contradiction, because there should be no non-trivial solutions to this, because these vectors are independent. Other questions?
Number 28.
Go home and read over this very, very slowly.
Says prove that in P subscript 2 every set W will then with more than 3 vectors is zero.
In P2, every subset
With more than 3 vectors is zero.
3 vectors is dependent. We actually talked about this a little bit last class as well. Well, I proved a specific example for
It just
this.
says every set, not subset.
Okay, what would be the proof? So let S equals B1, B2, B3, and more than that, Bn, be a set of vectors in P2. Consider the equation C1v1 plus C2v2 plus CNVN equals 0. What would that mean? We need to show that it's dependent. What do we do? We know what the guys in P2 look like, right? What do the guys in P2 look like? Give me an example of what a V1 would look like in P2.
It has 3 components or more.
What are they? Tell me what it looks like.
Polynomial
A polynomial of degree
2.
2. So what's a general formula for that? I can do something like A11 plus A12x plus A13x squared, right? Plus, I'm labeling these coefficients very suggestingly. Plus da da da. And over here, I'd have Cn times the guys in here would look like an1 plus an2x plus an3x squared, and that must be equal to 0 plus 0x plus 0x squared, which is my 0 vector in T2, right? Now, what this would lead to is a system of equations. This would lead to A11, A12, A11, A12, A13, A21, A22, A23, A31, A32, A33, A34, A31. I'm misnaming these guys. I'm doing the subscripts that makes it look like just a regular matrix that we've seen before. A12, A13, A14. A22. T1. Yeah, I'm trying to label these to look like 31. I had the order switch here. 1n, 2n, 3n. Okay, so let's get back on track. This is 2, 3, A2, 4. This is 3, 2, 3, 3, A3, 4. And I have at least this amount, right? More than 4 vectors, right? Now this is going to continue until I have A1n, A2n, A3n, and then I'm going to have 0, 0, 0, right? So my augmented matrix would have this form. Now, if you have an augmented matrix of that form, what's going to happen?
Free variable.
This means we can have, at most, right? The best case scenario. How many pivots can we have? 3 pivots. Which means we will have at least one free variable. Which means infinite solutions. Which means dependent. Why? Because independence requires a unique solution, in particular the trivial solution. Once I have infinite solutions, that's not the case anymore.
Are we supposed to end all of our proofs with that triangle?
That box thing, yeah.
Okay.
If you want to be classical, you can write QED.
I meant rectangular.
It's all the same numbers. Well, technically, it's not the same. Mathematically speaking.
Far.
Yeah.
Could you tell me where you got that part from? We can have the most three pivots. It's part of the equivalence theorem.
No. How would you have a pivot? You try to get one in the. You can have only one pivot per row, remember?
Oh, okay.
Because under each pivot, you has to have zeros.
Okay.
So at most, you can get 3. Right? Because they have to be in 3 different columns. But you run out of rows before you run out of columns. That's the point. Right? Which I did a specific example in R3 or R2, I don't remember, last class, where we saw the same thing happen. So you really want to extend on that. So again, like I said, when you're thinking about proofs, one thing is know the definitions, know what it means, know what it is that you want to set up. So I know that when I'm talking about dependent, what that means is this kind of equation has non-trivial solutions. So that's what I want to prove. Now to get to access that, I need to know the definition of what it means to be in P2, hence I plug that definition in. Being in P2 means you look like this. Once I see that, it means I can get to the matrix. And once I get to the matrix, this is chapter 1, it's all easy. Right? So it's about plugging in definitions, knowing what you want to prove, not begging the question while proving it. And using one of the proof techniques I talked about last time. Other questions? Yeah?
Do you have to like write it like that? Can you just like write it in words, like the explanation, or do you have to show it to the matrix?
Like how would you explain it in words?
Like, I'd say what I said was that P sub 2 has
3 unknowns. So if a P sub 2 had 4, then that would create a linear system that had 4 unknowns with only three equations that which would lead to a free pair.
That would be fun.
Yeah, I had the same question because I actually used definition of dimension instead, and kind of said like it exceeds the amount of vectors you're supposed to have to be linear independent.
That would also work, except we didn't technically talk.
Yeah.
Dimensions was in the next chapter. Did we talk about dimensions already in 4.3?
Next section. That's 4.3.
Because I think we didn't talk about dimensions on 4.5 is when you actually define dimension. I mean, when I mentioned it in class, I was sort of skipping ahead. So technically at this point, we wouldn't know about what dimension means. But definitely, if we had already covered 4.5 and I threw this on a test, you could have used that argument. It would be a cleaner argument to use actually. To say, well, we know that the dimension of this is 3, so if we have more than 3 vectors, that will be blah blah blah. The dimension argument. It's also a valid argument. Technically, it's ahead of this section. But by the time we get to the second test, that would be a perfectly valid argument for me.
Could you also set up a Wronskian?
Sure, yeah. So if we set up a Wronskian, we would have differentiate once at this point. In the second row, I would get a to 1 plus 2a3, and then at this point I would get 2a3, and then you could do that, but I see that you're running into trouble because you'd have this line here, these would all be constants, but you won't really know what they are. So, yeah.
I think
It could work, but I feel like it would be a lot harder to explain.
wrong. That doesn't find dependent linear dependency. It only finds linear independence.
Oh, well, the Wronskian theorem is an if and only if.
If and only.
Yeah, it goes in both directions.
I read the book. It was I remember from that case.
I think it's an if and only if. Yeah. So the Wronskian is non-zero if and only if. Of course, you have to be in a certain interval. Providing certain conditions, it's an if and only if. Other questions?
If it's 0, there could be 0 row,
A zero what?
rows of zeros. If determined is 0, there could be rows of zeros.
Yeah.
Then
That would, you'd be done at that point. But the thing is, it would be hard to prove that you can get that from using the Wronskian here, I think. Because your last line would be a bunch of constants. How do you know that they're all 0? You'd have to prove that you can reduce it to zeros. It would be harder. Not impossible, but I think it would be more work. Yeah, also explaining, technically we'd have more unknowns than equations, and so we'd have to get free variables. That's also fine. In general, though, explaining things in words are a lot harder, I think. Okay, 29, what does it say?
Please study the set V1, V2 is Ly, and V3 is not line span. V1, V2, then V1, V2.
Okay, so V1, V2 is linearly independent,
Yeah.
and V3 is not in the span. So let's say S is this, not. V3 is not in the span of S. Then
All three vectors are
V1, V2, V3 is linearly independent. I think you should have like these things over here. Okay, ideas.
Proof by contradiction.
Proof by contradiction is how I would do it as well. How do you set it up?
You first prove that it's
Consider-
I'll consider it's dependent, right?
So consider C1 V1 plus C2 V2 plus C3 V3 equals the 0 vector, and assume to the contrary. These are this V1, V2, V3 is dependent, okay? So if I assume it's dependent, right, which is not what I want to prove, so I'm assuming the opposite of what I want to prove, what would I get?
You could then solve either one of those for you could then solve any vector in that combination as a linear combination of the others. So you would solve for V3, right?
I'd want to solve for V3.
Yeah, you'd want to do that.
How do I know that I can?
You can, because you added together, right? And you're assuming they're dependent, so that means
Right, so dependent, technically what dependent means is there's a non-trivial solution. So I could have a 0 here and 2 non-zero numbers there. And then I wouldn't be able to solve for V3. How do I know that that case will never happen? Right? How do I know something like 1, 2, 0 could never happen? So yeah, V3 is who I want to solve for, but in order to solve for that, I need C3 to not be 0. There is a non-trivial solution for C1, C2, C3. Note,
that because
C3 cannot be 0 since y.
would that make it inconsistent?
No?
Matrix.
Since if C3 equals 0, then C1 V1 plus C2 V2 plus C3 V3 equals 0 would give what? C1 V1 plus C2 V2 equals 0. Right? And why would that be a problem? Because if I assume there's a non-trivial solution, and C3 is not a 0, it means that my non-trivial solution has to come from C1 and C2, which would mean
They have to
They are
be
not.
0 too.
That these two are not linearly independent, but I know they are. So this case can never happen.
You have to write that on the test.
Yes.
Yeah.
Right? So there are times when you know what you want to get to, but you have to be careful that you can't just assert that, yeah, this will happen and I can just solve for V3. No, yeah. How do you know you can solve for V3? Right? What about the situation where this is 0 and those are not? How do you know that won't happen? You have to explain this. Right? And would give C1 to da-da-da, and non-trivial solutions would contradict. Did I call that S? Yeah. Contradict S is a lie. So C3 is non-zero. And if C3 is non-zero, that means I can write C3 V3 equals minus C1 V1 plus minus C2 V2. And I can write V3 as minus C1 over C3. It's non-zero, so I can divide by it. Plus minus C2 over C3, V2. And that's a contradiction, because we assumed that V3 is not in the span of S, which means I cannot write it as a linear combination, but I just did. Was that it?
I had a question about the last rule, where you have to prove that a finite set that contains zero vector is linearly independent. Is that just the theorem we're going to use to prove that?
We actually use that theorem today, in fact. But yeah, so the thing is, if you have a 0 vector in a set of vectors, then what happens is you can choose 0 times everybody else. And then put a 1 in front of your 0 vector, and that will be a non-trivial solution. So as long as 0 is one of the guys in your list, a non-trivial solution would exist because his coefficient won't matter. And so you'll always be linearly dependent in that case. Because a non-trivial solution exists. In fact, an infinite number of solutions exist. I can put any non-zero number here I feel like, and it will be a solution. So having the 0 vector in a list automatically makes it dependent. Other questions?
And the part 2 to that? A set with exactly one vector is linear. Li.
Yeah.
If and only if that vector is not 0. So just prove my contradiction.
Yeah, and again, notice that I actually used that in the first problem I did. I said that if you have singleton sets, it has to be non-zero vectors in it in order to be independent. So the idea is if I have a set with one vector in it, then to check linear independence, what do I have to do? I have to set C1 V1 equals 0, right? Now if this guy is actually the 0 vector, right? If V1 is equal to the 0 vector, then I have non-trivial solutions. Right? Which means that that would be dependent. Because if this guy's a 0 vector, this guy could be anything. Right? That's from a theorem in 4.1. That's using the theorem that says if I have C1 U1 equals 0, then C1 equals 0, or U1 equals the 0 vector. If I say this is not true, it means that has to be true. And that's where you get independence from. stop there. You can pass the homework stuff. Want to finish 2 sections today, but that's not going to happen. We're going to have to speed things up, so I guess next week we won't have a quiz either. Which would give you guys extra time to read, because I know that some of the stuff I did today went over some of your heads. It's completely normal, doesn't mean you're stupid, but it does mean that you're going to have to start putting a lot of time into reading things very carefully and then really understanding what's going on. Because the class is going to feel a lot more like this from now on. So we've passed the threshold. And now we're going to talk about coordinates and bases. There was really one main example in this section I think I wanted to talk about. Let's give you some definitions. Let V be a vector space. What's a vector space? What's a vector space?
Plane containing vectors?
That's not a definition. That's a set of elements for which we define 2 operations, addition and scalar multiplication, that fulfills the 10 properties from section 4.1. That is a vector space. You need to know the definitions. You need to know the definitions. Okay, so V is a vector space, and let S be, let me actually define what this is. V1 up to Vn be a set of vectors in V. Then the set S is called a basis for V if 2 things are fulfilled. 1, S spans V, i.e. V is equal to the span of S, and 2, S is a linearly independent set. So if I have a set of vectors from a vector space and those vectors fulfill 2 conditions, I call them a basis. Examples again, I equals 1, 0, j equals 0, 1 form a basis for R2. Right? I proved that like twice already in this class. So example 2, 1, x squared forms a basis for P2. Example, if I look at these matrices, 1, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, form a basis for M2, 2. Right? Which means verification is left to the reader. Check that these 2 things happen. Right? How do I check if S spans V? What would that mean?
In the matrix and reduce it?
Nope, that's way too vague. What matrix? Reduce what?
V, I, and J put it equal to 0.
What does S span V mean? in English? A crisp sentence in English.
Linear combination of vectors of any vector of S would be, any vector of V.
Mhm.
You can write that as linear combination of vectors of S.
Yes. And how would I know that this is linearly independent? What does that mean?
Just the linear combination of S has to be 0. And
If you set a linear combination of vectors and S equals the 0 vector, then there's only the trivial solution. Okay. So basically you'd have to, if I asked you to prove that these are bases, you'd have to prove those two things. You have to prove that if I take any vector here, take any x comma y, I can write that as a linear combination of these guys. And that means setting up a vector in blah, 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 a matrix in blah, blah, blah. And if I have a linear combination of this, I can take any guy here, like an a0 plus a1x plus a2x squared, and I'd be able to write that as a linear combination of these guys. If I take any matrix in M22, A, B, C, D, I'd be able to express that as a linear combination of these guys. Right? And I have to check that these are also linearly independent, which means if I put coefficients in front of these, add them all together, set this equal to the 0 matrix, there will only be the trivial solution for the coefficients. You need to do those things. Right? So when you see all these words, they really mean something. You have to know what it means. Right? There's a lot of information going to be packed into a very small area. So some of you who are math majors, eventually, you get to classes where the textbook is like this thin. And you will take hours on a single page, because every little word will branch off into, it's not, Anyway. But you have to know what all these little words mean, or else you're going to really drown. Okay? There are some important theorems here. Suppose B equals B1 Bn is a basis, right? So I know ahead of time that this is a basis for a vector space V. Let V be in V. Then the solution for C1 to Cn in C1 V1 plus C2 V2 plus Cn Vn is unique. I.e., for a given basis, V in V can be expressed as a linear combination in exactly one way. Right? You will not have two different solutions giving you a vector, right? It has to be unique. So if you have a basis and you're using that basis to describe any vector in your set, you can only do it in one way, right? You will not find another way to do it. Let's prove this actually, because proving uniqueness is something that you often do in math, and so you should sort of know a technique for it. The idea is when you want to prove that something is unique, that there's only one, what you do is pretend there are two, and show that that's impossible. Proof. Assume V equals C1 V1 plus C2 V2 plus Cn Vn. And at the same time, there's another way to express V as K1 V1 plus K2 V2 plus KNVN. And assume KI not equal to CI for some I. What kind of proof am I doing? Contradiction. Okay, which means I need to somehow get to a point where, assuming that doesn't make any sense. How do you see that?
Deduct two vectors from each other. K1 vector V1 plus K2 vector.
Right, now this means, let's say here I call this equation 1, call this equation 2, I can say subtracting 1 from 2 gives K1 minus C1 V1 plus K2 minus C2 V2 plus Kn minus Cn Vn equals the zero vector, which means
All of them has to be 0.
they all have to be 0. Why?
Because V1 is linearly independent.
Yes, these v's come from a basis, which means they're linearly independent, which means setting up an equation like this guarantees that the coefficients have to all be 0. So this would mean that K1 equals C1, K2 equals C2, and in fact, all such Kn equals Cn. That's a contradiction, which means it's unique. There's no way I can express these two in a different way. And that uniqueness is what leads us to the idea of coordinates. Which means if I talk about a vector in a random vector space in terms of a particular basis, the set of constants that I can set up a linear combination for a random vector will be unique. And because it's unique, I can sort of think of this as an identifier. There's only one location for any given object. And that's where the idea of a coordinate comes in. So suppose B equals B1 up to Bn is a basis for B. Then for any V in V, we have a unique equation C1 V1 plus C2 V2 plus Cn Vn equals that vector V. The vector C1, C2, Cn, remember these guys will be unique. Well, let's call it, let's use that. Is called the coordinate of. And so I'm defining the phrase coordinate, that's why I'm underlining. Coordinate of V with respect to B. Which may be denoted, if I want to emphasize what basis I'm talking about, if there are several ones that I'm considering all at once, I could write V with a subscript B equals that coordinate, C1, C2, C2. example. Notice in R2, any vector here I can write as A times I plus B times J, which means I can consider the coordinate AB to be the coordinate of, call this vector B, equals coordinate of B. This is the reason why a lot of times in Calc 3 students mix up coordinates with vectors, and that's why I started writing this kind of notation for vectors. In general though, in higher mathematics, you always use parentheses. Eventually you'll get to the point where you won't confuse when you should be thinking of something as a vector instead of something as a coordinate. But yeah, so why they look the same is because of the basis that we were using, right? It's not always the case that it will be that easy. So, note the set S equals one minus 1 minus 2, 2, 1, 1, 0, 1, 1, forms the basis for R3. We proved this in pieces. We proved, when I talked about linear independence, we proved that this was linear independence. And when I talked about span, we actually proved that this spanned the set. So this is an example we've been thinking about for a long time. So now let's bring up our idea of coordinates into this with this example. So A, find the coordinate of 1, 2, 3. Find the coordinate of the point 1, 2, 3 with respect to S3. So the coordinate of 1, 2, 3 with respect to I, J, K is just 1, 2, 3. But what is it with respect to this basis? Right? Give me the coordinates. B. What vector in R3 call it B, will we have its coordinate in terms of S is the vector 4, 5, 6. Try that on your own, and we'll do it next time. Remember to leave your homework. Okay.